Hi, welcome to this video on Labyrinth of Douglas on futureskill.com. So I'm gonna go through a possible solution, a way to solve it if you want. On futureskill.com I'm gonna show the interface. I'm also gonna draw a bit and show on the whiteboard that I have, or actually iPad, which doubles as a whiteboard. And then in the end my plan is to look a little bit at ChatGPT and how you might go about starting. I'm not going to go the full route with ChatGPT. I'm going to focus on showing a solution I already have for the problem. So if we go to, there's a previous video where I explained the problem. So I'm not going to go through that again. Please check the video, which is in close relation to this one. But this is the problem we have. Katniss trying to get to the star, and Douglas trying to capture the cat. So cat wants to go to the star, Douglas wants to go to the cat. And if we look at the interface, it looks like this. So we have the description here. We have an API, which I also went through in the other video. So here we have the solution. So this is where I'm going to focus right now. And when we have a working solution in the end, this level 1, let's press run code. Then we'll see, we get the confetti. Then we'll see the solution being run like this. And in the end, Katniss will reach the star. So how do we do this? So I'm going to just show this with Python, but of course the solution is possible to translate to any language. So we have a solution class here given to us initially with the API being set. Then we do some calls to the API to get the width and the height of the playing field. We save the vertical walls and the horizontal walls. And because of a choice here, I'm using getIndex. So what that is, you can see it right here. It just translates the chords to the index. So if we show that, since that's a part of this solution, I can show it here. Let's move the cat and dog aside a little bit for now. So this first square is 0,1, and then we have 0,2. I mean, we can see that if we go here and we press the XY, we see 0,0. It was 1,0, 2,0. It was good I did that. I started off the whole. Where did I get 0,0? So it should start with 0,0, then the X value increases to 1,0, 2,0, and so forth. And if we go down, then we have instead 0,1. The Y value increases, and here is 1,1. But the indexes that I use look a little bit different. So I just use index 0, 1, 2, 3, 4, 5, 6, and so forth, all the way down to 15 here at the bottom right. So for me, just a little bit easier to see something like 3 than to see something like 3,0. And also it was, the way it was done originally was using these indexes, so that's the main reason. But just want to explain why I'm doing conversion here to these indexes from the API's X, Y values that I get in here. And also for goal, I convert that one from the API to an index. Then we have a path cache. That's just basically when we have solved it, we put the solution into a list. And then we have some current index in that path cache. So that we are doing right now. So get chords is the opposite of get index. So that's going from an index and calculating X, Y, or col, row, and returning it as a tuple, like so. It's also important that it is a tuple and not a list in the end, because we're going to use that as in the cache to do the lookup on, and then it has to be immutable or not possible to change like a list. So that's why we're using a tuple. Get index we saw was the other way around. We go from an X, Y and return an index according to what I just described. And then if we first, so now I've described the constructor and some methods here. Then let's look at what the overall idea is. We have one method called valid moves that calculates from a certain position where can we go. Especially this is valid moves for Katniss actually. I don't think it's used for Douglas. So we send in a position and we want to get a list of all the positions that we can end up in after doing a valid move. And as we see here, standing put, doing a passing move is always a solution. Or always a possibility, always a valid move. Then we have a Douglas move. So I'm going to go through it more. But first let's look at what these ones do, the methods. So we have Douglas move, then we send in where Katniss is currently and where Douglas is. And then we want to have the next move that Douglas would do in this situation. So we actually need to call this twice to get Douglas both moves in each step. But that's the idea with Douglas move. Then we have breadth first search. So that is a recursive method that where we call ourselves. Or am I lying? Yeah, I'm lying. It's not recursive. Okay. Yeah, we are using, instead of doing recursive calls, we are working off of a queue, which is basically a list. But this implementation is called deck, which I actually found out about while using ChatGPT. I hadn't used it before, but it's basically a list which is very quick to do insertions and popping both at the front and the end of it. At the lowest index and the highest index is quick to add new things and to remove pop off things. So here we are doing the actual tree search anyway, to try to find a possible solution for Katniss. So this is maybe the most important method. Then we have make move. So this is one given to us by the interface. I mean, this is the starting point. We have to have the make move method. The idea is that this is one is called over and over again, where with the current position of Katniss and Douglas, and then we should give the next move. In practice, though, we're gonna save the solution that we get from breadth first search into a path cache. So we only call the tree search once, and then we reuse that solution for each time that make move is called, which maybe is the more logical thing. So those are the different methods that we have. So if we start off here at the beginning where we were, we can look at valid moves. So we send in the position as an index. We always put in the current position. The passing move is always valid. And then we check if we can walk to the left. So position -1 is then a move to the left using these indexes, the orange ones that I described here, 0, 1, 2, 3. So if we go to the left, we decrease the index by 1. That's what we're doing here. And then we're checking. I'm not going to go through in extreme detail here, but that's left to the reader, let's say. I'm also checking that in the end is a valid move. We don't move outside of the boundaries. We don't also walk through a vertical wall, so we have to check that. And then we do the same thing going to the right. It's always increasing the index, the position. We do the same kind of checks with vertical walls. And then we check if we can go up, position minus self.width. If we look back here, the width of the this example one that I have here is 4. So if we are at index 4 and want to move up, we take minus the width, -4. So we go to position 0. So we're looking there for a move up. And then we check if that's valid. So we can't move through walls. We can't move outside of the top of the labyrinth. And then we do a very similar thing here where we increase by width, meaning we try to do a step down in the labyrinth. And then we check for walls, check that we don't go out. And then we return moves. So that is valid moves for Katniss. Maybe it's used also for Douglas. I'm not sure. I don't think so, but no. So Douglas move is one of Douglas's 2 moves. If we look here, it's used to calculate, like here he does 2 moves to the right and then up. So Douglas move is called twice here, we can see. So it's called, So this is just one step for Douglas that we're calculating here. So there we're going actually the other way. Here I could have used the XY conversion, get chords, but I'm apparently doing the same calculation again to go from the index to X value and to Y value, and from Katniss also going to X and Y value. And then we're checking first if a horizontal move is possible. So do we get any closer by going horizontally? And that we don't go through the wall. Then we return a horizontal move to the right. And then here we check if we should move horizontally to the left. That we don't go through any walls, and that we end up closer. And then we just return that move to the left. And then we do, if that's not possible, then we check vertical movements. And first here we check plus width. So here we check going down, if that brings us closer and if it's valid. And then we return it if it is. Otherwise we check going up, and if that is possible, we return that. And if no move is possible, we stay in place and do a pausing move with Douglas. So one of those little pausing symbols there. So that is Douglas moves. So now we come to the very this is the actual solution here, as we can see, is very short, which is nice. So we start by building a list of all positions to search from. And here we should go to the whiteboard here to just so I can show what the idea is with the tree search. So it's maybe not called tree search, it's called breadth first search. So what the idea is that we start off with some position here, and this position is a certain index for Katniss and for Douglas. So these are integers, or the indexes that I'm using in the in the code. So we have two indexes in a tuple like this, defines the position entirely. This is always the status. Well, it's the state that we have initially. Katniss and Douglas is standing somewhere, and whenever they have both moved, we also get to something like this, and it defines entirely the state, so to say, which is an important realization. Like when you have them in a certain position here, that is, there is no more information to be had. This is how they are currently standing. So each of these is one of the possible states that we might end up in. So this is a node of the tree, and then we have possible moves to make. So if we call this one K1, D1. So let's say we can move with Katniss to some new place, and then Douglas will move. Then we have K2, D2. And we'll have something similar here in each of these nodes. What is K2, D2? Well, that is just, if we start from the beginning here, where do I have my, we are at the beginning now. So this is the initial position. So this is defined by, well, I'm using indexes, so it would be 1, 12, I think. And then we do one move with Katniss going there. So here we go to 5, and Douglas ends up in 13. Now, it would be a different state, of course, if Katniss had moved to 5 and Douglas would now be, for example, here in 3,1. That would be a different state, but this is exactly the state after this move. So this is a new node in our tree where we're going to search from. And that's what we're looking at here. And then we simply continue. So we create new moves. We try valid moves for Katniss. And we go further down the tree. And we check out for a position where some things break the tree. So one thing that can happen is that Katniss is caught. So we are moving here maybe to a location, and then Douglas moves to the same location. That one we can just break off. We can't continue anymore. We are caught. But what we're looking for is, of course, something like here, let's say, here maybe we reach the star and Douglas is not on the star. Then we have solved it. So that's what we're looking for. And as soon as that's happened, we return. Now, one problem that we definitely have to solve is that this was the starting position. And if we go down here, then there's a new position. And if I would go up again to 1,0, maybe I can use interact instead to make this point. So let's say I go down here, Douglas goes here. So this is a new unique position. If I go up here, it's actually also a new unique position, because Douglas was here before and now he's here. It's actually a worse position, but it's a new position. It's a new state. If I go down here, that's a part of the tree that we don't want to look at, because then this search will explode. And the reason is that this is exactly the same position that I had 2 moves ago. So I stopped there and Douglas was stopping here. So we want to avoid continuing with the tree whenever we have exactly the same state. So that's an extremely important thing to do. Otherwise the search, like I said, will explode. So we want something like, maybe here and maybe here we've already visited, let's say. Then we want to stop the search there. And we just want to continue with any new states that we find. The queue that we have here is for, now I have to think where I was just explaining. Yeah, the queue here is for, it's a list of all the places where we still have to search from. So these are all nodes in the tree. So these are all the remaining places where we still haven't looked through entirely. And it starts with the starting position of Katniss, Douglas. Then we have a visited set here. So that's a set of all the locations, all the states that we have already seen. So this is the starting state. We are starting from that one. We don't want to go back to it. If we ever end up in the place where Katniss and Douglas are in the same places that they were from the start, then we don't continue the tree from that point. That's the point of having this cache, this visited. So set is nice. It's just, we don't need any, like a dictionary, we don't need any values. It's just like a hash to look through if there is, and it's an extremely quick order 1 lookup. We use an immutable data type as tuple of 2 integers, which is important. Then we have while queue. So while there's still some nodes left in the tree to search from, so if we have something like this and we have this one we haven't looked through and this one we haven't looked through, then we want to continue. Those would still be in the queue. If this one is empty and we haven't returned, we haven't found any solution, then we're going to return an empty list. And that is the case where the labyrinth, the problem is unsolvable. It's very easy to create a problem like that. For example, if we look at this one here and we remove this hiding spot or this place for Douglas to get stuck on, so it would just be a straight line here, then it would not be solvable. Then we would return an empty list. So that's what we're doing here if we don't find a solution. But while there is still nodes or states to look through, then we pop left from that one. So we are lifting out the index where Katniss is, the index where Douglas is, and also the current path to get there. So this path is used so we get the solution in the end. So it's a memory of the steps that we have taken to get exactly to this state. This is the solution, which we will, when we see a return here, we return the path. So that will actually happen right now. If Katniss is at the goal, we basically print success and then we return the path. So this part here with all the steps. I mean, if we run the code here, we will see such a printout. So here we see a way to walk to the end. And this is basically a list of tuples of all the steps that we took. The first step was 5,13. That's where we started. Then we went with Katniss to index 6. Douglas ended up at 14. Katniss went to 7. Douglas ended up at 11. And so forth. All the way to 2,4. So in the end, Katniss here is at index 0, 1, 2. And Douglas is at 3, 4, index 4 here. So this is our solution that we are saving in the path. So in other words, if we look at this tree, then we said that we found a solution here. The path basically contains all these nodes, all the states that were necessary to reach this solution. Then we look at, we generate all the valid moves from Katniss that we saw up here, this one. So where can we go from here? We can always do a passing move, for example. And we check those indexes that we can go to. After Katniss has made a move, Douglas makes 2 moves. So first he goes somewhere. We get temp Douglas is where he would end up. So then we send in the new location where Douglas would end up. And then we see that he would actually end up in this index here after 2 moves. If they are the same, then Douglas caught Katniss, as it says here. We just continue. I guess we could have saved this also in the queue, or in the visited, but yeah, we just continue, meaning we continue with the for loop here. If that one is done, it's no more moves to look at, then we will continue with this while loop here. But if we are not caught, then we know, well, then we can check versus the visited cache and see if we already looked at this node of the tree. So again, going back here, we said that when we did a pink cross here, then we had reached that one. If we somehow via different steps get back to this one, then we skip and do not continue evaluating that path. For example, just making passing moves will quickly end up in the same position that we just were in. So then we skip and continue. But if it was not visited, then we have a new location, new state. So then we add the new Katniss position, the new Douglas position to that set. So we know to not go there again. And then we have a new node now we're building downwards in the tree. So we're going, basically jumping from some location here, let's say, to some new location here. Or going from here to here, going from here to here. Then we're going down the tree, exploring new possibilities. So then we, in our list, in our deck or queue, we append the new position of Katniss, the new position of Douglas, and the path we had before, plus the new step that we took to reach it. And that's basically it. So this is using a list or a queue. It's a way to traverse the whole tree that we have, like so. And yeah, if there's no solution, we'll return an empty list. If there is a solution, we will return it. And we'll return the full path to it, like so. So this is the interesting part to get through and to analyze. It's actually not that much code necessary to solve this. It does also solve the big one, which is, I think, 9 by 9. Although it takes a little bit longer, but because we are using a cache for visited, it's not super slow also. So I'm not going to go through all of it, but if you jump to the end here, you can see how Katniss eventually has fooled Douglas to get stuck, and then in some 120 moves or so, we reach the star. And what happens is that in many cases we end up in the same place as before. So we're helped a lot by this cache here. If I remove that one, for sure it would never return in time. Okay, so the make move then, that's simply, this is the one we get given from the code. We start off by converting the positions to indexes, since we're using indexes or integers here for positions instead of x, y. Either we have already solved it, we have a cache, and then we just we decrement the index, and we why do I do this? Okay, if there is a cache, I'm not sure what this is actually, but basically we just take the next step. If we are not at the end of the cache, then we convert the next step here from the path cache to coordinates, turn them into a list instead of a tuple, and return that one. So yeah, if there is some bug or something, then we just return 1,1. That should not happen. Maybe it happens if it's unsolvable, for example. Yeah, then we would return an invalid move. But But yeah, if it's not solved, then we call breadth first search, the tree search that we just looked at with the initial solution, and we get path cache. Unless there is no solution found, and then we also return an invalid move here. But basically, just one call to this one. And then in the last one here, we are called here 124 times, but we just return the next step in our cache here. Oh yeah, we only go in here, of course. Yeah, I read the else statement wrong. That's why I was confused. So we just back off. Okay, we set it to -1, so that the first time then it goes up to 0. So this one will always give the index 0 and then index 1, 2, 3, 4 in the list of the solution. So first we send this one, next call to make move we send this one, and then this one, and so forth until we reach the very end here. And that is one possible solution for the Labyrinth of Douglas. And you can of course solve it in any other language here. If you just change, it will give you the skeleton code for the other language. It works just the same, but of course you have to do it in that language. And yeah, good luck in solving this one. As a bonus, we can look at how to do with ChatGPT. If I'm going to solve it with ChatGPT, the initial part would be to copy the description, copy the API, all the information here, and also the starting code. So if we go to Python and go to the initial state, I would also send in this. And that's what I've done here. So I sent in all this text here to ChatGPT and asked it to do a Python solution utilizing tree search with a visited squares cache was the instructions. And it does some rationalization, and if we copy this one, it will actually not solve it from the get-go. You have to work a little bit with it, but that's not what this video was supposed to be about. But I mean, it does a good try to get started. Let's see, did it solve it? No, the cat is just standing still. Yeah, that would have been surprising. But you have to work with this and maybe end up with something like what we had before. I mean, you can see here it's very similar to what we had. There is a visited structure here. And I think actually the solution I shown, I think I started with ChatGPT to do it. So maybe it's not that much needed. You need to do some debug printouts and see where it goes wrong. Surely it's misunderstood the problem in some way on how they move. So I mean, how are the walls positioned? That would be a place to start to solve it using ChatGPT or some other AI. Yeah, thank you for watching this video and good luck solving.